of our modeling. Our next major item is to look at what are called continua, fields, and the corresponding state space corresponding to continua. Okay, so what the heck is a continuum? In many situations that we are interested in, we need to consider systems that have many parts. If you have a box of gas, it's got Avogadro number of particles. So for example, if you look at this pen, and I want to say, okay, the molecules of the pen, it's too many and they're also too complicated, right? And I may not need all that information about every molecule. I don't really care about if you think about, okay, will this pen write well or not? That's my interest. Or how should I redesign this pen? I may not need to know much about where are the molecules in this pen. Okay, so that's something to think about. So what we do is we smear out the molecules so that it's completely obliterated, and the material in the pen will now be assumed to be filling everything with no gaps. If it is molecules, you know that there will be gaps, right? Quantized, lumps. So molecules are lumpy, and lumpy things will have gaps, and we want to make sure that there are no gaps. So that's our first idealization. Why do we like that? Because we can use the tools of calculus. The price you pay will be quite a level of abstraction and some problems, but the advantage is you can use the tools of calculus. So that is the trade-off. Okay, what the heck is a continuum? A continuum is, roughly speaking, a representation of a system with no gaps. What the heck do we mean by that? It means you cannot, if you take this object, if I think of it as a continuum, I cannot cut it without some common part. So the cut portions will have some common part that is shared between them. For example, if I have only 3 particles, if I have only 3 particles, you can see the gaps between them, right? So I can cut it and they will have no shared objects at all. On the other hand, if I have a lump of material which is completely occupied, if I cut it, along the cut, the particles will have to be shared. That's what we mean by continuum. Right? This is the intuitive idea. In a mathematical framework, it's actually a fairly complicated thing, and so I will not go into that. By the way, it does not have anything to do with functions or state variables being continuous. So that is a different idea, although it uses the same word. So be very careful when people say continuum mechanics or continuum means things have to be continuous. That's not the case. Continuum means that there are no gaps. Right? So be careful. So be careful about how you think about it. Continua can have different discontinuous state variables. So please remember that. Okay. Okay. So if you have a continuum, there's the lump. You can cut it into 2, and there will be a common region. This is called the contact surface. The common region when you cut things into 2, and now you have 2 separate continua, and these will be called sub-bodies. So this will be called body, and this will be called sub-body. And the nice property of a continuum is you can go on slicing and dicing it until you start getting small chunks. You can see the calculus how it comes, right? Because of the fact that unlike a discrete particle where beyond a certain level you cannot cut it any further, in a continuum you can go on slicing. That's why calculus works. Okay, so the stuff inside the continuum is supposed to be made up of particles. What the heck is a particle? I don't know. It is the stuff inside the continuum. What about the boundary? That will be called boundary particles, right? The stuff. So continuum has 2 parts. The continua that we are looking at will have a part which is called interior and a part which is called surface. So there will be the stuff that makes up the surface will be called surface particles. The stuff that makes up the interior will be called interior particles. There will be an uncountably infinite number of particles in a continuum because every point in the interior there is a particle. By the way, the only attribute that a particle can have is position vector and type of particle. It cannot have mass, cannot have momentum, none of the interesting properties you can attribute to the particle. So it's very limited in what you can do to it. And the reason for that is because mass and momentum and all of that, if each particle has mass, uncountably infinite number of particles, so if the total mass of the body will become infinite. So this is actually a problem. So we have to approach mass and other properties in a different way than what we do. Okay, so this is the price you pay for making something into a continuum. Okay, so how do we deal with all of this? So the next thing is to start talking about. So now we have a cartoon, right? Our primary attribute is the fact that it occupies some space and it has some boundary. So those are the two things that we are capturing, right? So the attributes that we are capturing is occupy space, with no gaps, and with boundary. Very nice. So, in order to talk about the space of a continuum, you have to introduce what is called a field variable. A field variable is a state variable that is attributed to every particle in a continuum. For example, when we talk about a temperature field, T of x comma T, it says temperature at particle x at time t. So even our field variables become infinite dimensional because there is a field variable value at every location inside the continuum. So you can see that that we seem to have gone from the frying pan into the fire. You know, I told you 6.023 times 10 to the 23 is bad. Well, infinity is really bad. But the nice thing is, calculus enables us to conquer infinity in a way that we cannot conquer 6.023 times 10 to the 23. So infinity is not bad because it's a nice idealization that allows us to do a lot of shady things in the name of calculus. That's the advantage. Okay, so that's why I told you it's a cartoon, so don't take it as reality. So mass, momentum, energy, you cannot do anything to particles. They are not field variables. Mass, momentum, energy are not field variables. You cannot attribute them to particles. We have to do something else. And so remember, this is not reality, it's only a model of reality. So now we come into the fact that a continuum has two kinds of state variables. Intensive variables, also called fields, position vector, temperature, that make sense as field variables. Extensive variables, technical name for them is measure. They are variables that are defined only for subsystems and not particles. What I mean by that is, if you take a whole body, I can talk about mass of a body. I can talk about mass of any chunk of the body. But I cannot talk about mass of particle. Mass of particle, I cannot talk about it. So we are now closer to the fact that there are two kinds of things. All our interesting mechanical properties are attributed not to the particles but to the body. But if you do that, you cannot do much in way of calculus. Calculus only works with field variables. So how the heck do we convert this into that? So we have a way of doing that, and that's actually a very interesting approach. So by the way, before we go, key extensive variables: mass, momentum vector, internal energy, kinetic energy. These are key extensive variables. These are defined for chunks. So please remember that, okay? But there is a way to convert measures into field variables, and that is by taking ratios. So what I will do is, here is my object, that's the body. Here is the point in which I want to define a field variable that corresponds to mass. What I will do is, I'll draw a circle. Okay, so I know volume, so mass of circle divided by volume of sphere. Right? If you take this ratio, you'll get a number. Now what you do is, you go on drawing concentric circles or concentric spheres that get smaller and smaller and smaller towards a particle, and so this will become limit volume goes to 0 of mass divided by volume of sphere. That will be called the density, mass density or mass intensity. That's equal to density of the particle. So now this thing I can do for every point. I pick a point and I draw circles. I pick a point, I draw circles. Pick a point, draw circles. So every point I can do that, and in principle I will get a field variable. That will be called mass density or mass intensity. So please remember, mass intensity is at a particle, not of a particle, at a particle. And it tells you how concentrated the mass is. So high mass intensity or high density does not mean the body is heavy. It means that the mass is concentrated. Right? So it is mass concentration or mass intensity. Same way you can do for any measure. You can take limit of momentum divided by volume. That's momentum density. And or momentum intensity, that tells you how concentrated the momentum is. The symbol for that is P. The symbol for mass density is rho. This will be a function of x and t. This will be a function of x and t. So if you want to say, hey, wait a minute, how do I get back the original measure? It's interesting, by integration. Rho x comma t dv, p x comma t dv will give you total momentum, total mass. You can see where calculus comes in, right? So this is the idea, how we convert measures into fields. So anytime you have something that's measurable, you can do that into a field. Now I've done this in a very sloppy way. So there are a number of criteria for which it has to meet so that it makes sense. The principal criterion being that if you have two bodies which are disconnected, the mass of the combination of two bodies must be equal to sum of the masses. Otherwise this will not work, because remember, integration is summation, right? So for the summation and other things to work, you need to have that. Okay, so that's how we convert measures into specific quantities or intensity. So now we have everything as field variables. What about on the surface? We will talk about that when we get into purely mechanical systems. So our next topic is purely mechanical systems, where we are not interested in thermal and other things. We're just looking at mechanical response. What are we interested in? Science question is predict the motion, i.e. position vector of the particles as a function of time of a continuum. How do we do that? That's the science question. Engineering question is control the motion of the system so that it does what we want. If there is only a few particles, then I can do a variety of path planning strategies. We know how to do it. This is what you learn in a statics and dynamics class. All of this stuff here, that's about controlling motion with very few attributes. And when you want to control something, what control levers and knobs do I have? So this is where we come to the question of what is the stimulus and what's the response. So this is automatic to any control problem. You have to know what's the input and what's the output. Right? So this is a very fundamental thing. This is not there in just a description problem. There's no clear distinction between input and output because you're not trying to do anything to it. But in a control problem, you have to have an idea what's the input, what's the output, and what's the relation. So that's where we are headed. So brings us external mechanical stimuli on a continuum. So first thing is system interacts with the surroundings. So here is your system. Here is the surrounding. Somehow there is some interaction. And the key state variable is force. That's the mechanical state variable that we are interested in. That's our control variable. That's how we push or pull or whatever we do things. Okay. Now, as with the other variables in a continuum force comes in two flavors. Field variables, direct body forces, like gravity and things like that, which act on each particle directly. It's always problematic to think about gravity and other things that way, but that's how we are going to think about it. Okay, so the gravitational force in each particle is density times the gravitational acceleration. Okay, the other one is things that happen through the surface at the common interface. You remember there was a common interface that was shared. Things that happen through that is called contact forces. Right? And the idea is that they are additive over the surface. So if contact force over this region is known and the contact force over that region is known, the total contact force is the sum of these two things. Obvious things, no? So that's an additive. But the minute you do that, you can talk about contact force intensity. So the force intensity is called traction. Just like density equals mass over volume, that is mass intensity, traction is force vector over area, and that's force intensity vector. This is called traction vector. So if you have a point here, there's a surface, and there's a force acting on the surface, F over A equals T, that's the traction vector acting on the surface A. And it comes in two flavors. One is normal, perpendicular to the surface. So of course that's nothing more than just a resolution of the force. So you got a force F, you got something that's perpendicular, something that's parallel. The one that's perpendicular surface is called pressure or normal stress. Actually you should say normal force intensity, and this one is traction or shear stress, shear force intensity. This is what drives the system. So the way you interact with it is by applying these forces. So this is our input to the body. Output is how the body moves. Okay, so that's where we are going to be, and then next class we will talk about how these things are related. Thank you very much.